All right, welcome to section 8.5. You might have noticed that 8.5 is kind of a special section because it has its own homework. No other section has its own homework. Usually we have several sections, maybe even more than one chapter in the homework. But partial fraction decomposition is a pretty labor-intensive process. It's part of chapter 8. By the way, notice the name of chapter 8, Systems of Equations and Inequalities. Not really. That's not really what really what partial fraction decomposition is. It's just that it can lead to a system of equations. And we'll talk about dealing with that. I almost feel like I should give you an example but let's go ahead. Decompose. I'll explain what that is, but we're decomposing a polynomial that has a fraction that has in the denominator a polynomial that has non-repeated, meaning unique linear factors. And so I'm talking about like something like x over x plus 2, x minus 3. These are linear because of degree 1. And they're not repeated. I don't have a square or anything, which is exactly what happens here. When they say repeated, it would be like x over x plus 2, x plus 3 to some power. They could both be to a power. But that would be a problem with repeated linear factors. And then you have irreducible quadratic factors. An irreducible quadratic factor would be if I had x over, and let's say I had x squared plus 2. So notice where the square is. It's inside the parentheses, it's inside the factor, and so I cannot factor that further into just, x and x. So when we say quadratic, we mean degree 2. And irreducible just means I can't factor it. But also notice how it's crossed out. I'm not going to have us decompose this. As labor intensive as these are, it gets even, might get even harder on these. And then what are we talking about for the case 4 that we're also going to skip? Repeated irreducible quadratics. So that would be if I had x squared plus 2 squared. All right, so we might do something like these first two, but these last, not so much. All right, still haven't told you what decompose means. So let's just get into it with an example, and I think that's probably the best thing to do. So you're given a polynomial, and it does have to be of, reduced to its lowest form, meaning if I multiply this polynomial out, in fact, that's actually something I sometimes will, something I definitely want to point out here. Sometimes you'll be given the problem not factored. Now, most of our problems are factored, but if you're given to it like this, your job is going to be to repackage it so the denominator is factored. All right. Then our goal is to take that problem with a factored denominator and write it this way. A over one of the factors plus B over the other factor. And this is just what you put over linear factors. You put a single letter of the alphabet like A or B or C over the factor. And that's actually what the theorem that they wrote out here is stating. If you have a factored polynomial in the denominator, like what? Like x minus 3, x plus 1, the role of the numerator is just that it can't be of higher degree than or equal. It has to be a lower degree than the denominator. So don't even really care what's up here. for now. We're just looking at the denominator. That means we can write it as x minus 3 times x plus 1 put question marks up, doesn't matter what's up there. And I'm just going to say a plus b, and if there was another one, c. So I know I'm writing on top of my rule here, but the rule gets pretty messy when you just look at it with all the subscripts and everything. So let's to see it in practice, it's pretty straightforward. What am I doing to this x? Ignoring it. What am I doing with this x minus 3? I'm putting an a on top of it. And what am I doing with this x plus 1 after the plus sign? I'm putting a b on top of it. So that's, in a nutshell, what they're trying to say up here. So we want our problem with a factored denominator and our setup. And we're going to clear fractions. So clearing fractions on this particular problem is just that. I'm going to multiply by the LCM, which is the denominator. And let me cover this up here. All right. So I'm clearing fractions. So I'm multiplying by everything by x minus 3 times x plus 1. So if I multiply this by the LCM, the entire denominator cancels and I just get x. If I multiply this term, this whole fraction, by that, the x minus 3's cancel, and I'm left with a times x plus 1. If I multiply b, this time the x plus 1 cancels. I get b times x minus 3. Now, if it helps you, on your scratch work to actually write it out next to every term, if you find yourself not canceling properly, that's probably not a bad idea. So you can actually see it happen, but I didn't bother doing that every step. But all right, so we get, if I distribute this, bx minus 3, distribute this, ax plus a. And I didn't really distribute here, but it is going to be important for me to recognize this x on this side, this polynomial, as 1x plus 0. So I went ahead and wrote it already a little early, a little before I needed it. But x has an invisible 1. If I were to write this as a polynomial, for example, in long division or something, or synthetic division, I would have to be aware of these exponents or these coefficients, and I do this time. All right, so all I did here was rearrange things. I took this bx and put them together, so the x's are next to each other, the constant terms are next to each other, and I even factored out the x, put the parentheses around here for emphasis, and I want to just look at this whole thing. And I want to do something called equating coefficients. So the coefficients on both sides of the equal sign have to be the same. So for degree 1, on this side, the coefficient is 1. And on this side, the coefficient of x is a plus b. For degree 0, it's 0. So what that does, and the reason why this whole chapter, or this whole section is in chapter 8, is that gives me a system of equations. A plus b equals this one right here, and I write that as an equation. But also a minus 3b is equal to this 0, and I can write that as an equation. Well, if I have an equation like that, I can use the elimination method. And the elimination method would have me multiply this by, well, there are more ways to do it than just this, but when I looked at it, I said, how nice would it be for those b's to cancel? So if I multiply by 3, I'll get 3a plus 3b equals 3. That creates this cancellation, and that gives me a equals 3/4. Once I know that, I can recopy, I can back substitute it. Once I know a is equal to 3/4, I substitute it into this equation. It's called back substitution. So a plus b equals 1 becomes 3/4 plus b equals 1, and I get b equals 1/4. So what is the conclusion? A is 3/4, b is 1/4. Let's go back to the beginning where I had this a over b. And I'll just erase what I have there. A I can replace with 3/4, and b I can replace with 1/4. So what we did was we kind of considered, if this was the answer, what was the question? If this was the answer, what was added together to give me that answer? And that's what decomposition is. Decomposition is when you take something and you write it as a sum. And you probably did this when you were 6, 7, 8 years old. The first example of decomposition that most students ever learn is something like 357 is equal to 300 plus 50 plus 7. What are you doing? You're decomposing it into individual place values. And the 3 means 300, the 50 means 7, the 5 means 50. And that's very different than 753. Because even though 753 uses the same numbers, 7 doesn't mean 7 ones, it means 7 hundreds. All right, not to give you a early education lesson here, elementary education lesson here, but this is also called decomposition. It's decomposing by place value. We're obviously doing something far more complicated than that, but if you take something and you say, this is the answer, what was a question in terms of blank plus maybe blank, that's the classic idea of decomposition. And we did it here, all right? So we see what we got, all right. So, case 2, let me just write this out. So the difference between the one I just did and this one with repeated linear terms is this exponent right here. When you have a square, sorry, I'm off the page, off the screen. I circled that too right there. When you have a square on a problem, it means that, get this out of the way here. It means that that is a repeated value. So I wouldn't want to think of this as x squared over x minus 4, x minus 4, x plus 5. I mean, it is, but I need to square it to capture that repeated value. Once I realize that's what it is, my setup is going to be, well, as outlined by this a little bit awkward way of writing it, where they use these A's, ones, I'm going to use A, B, and C, but basically it's this. And when you see it set up, it should be fairly straightforward. All right, so I take the x plus 5. I know this is the answer to a question, but what is it? Well, it's x plus 5 with a number on top of it, and that number I'm representing with A. X plus 4, so I take this linear term and write it once, not with exponents on it, but just x plus 4, and a number on top of that. And then I write x plus 4 again to the next higher power. Now, If this had been a 3, I would have added a d over x minus 4 cubed to the list. That wasn't the case, but just want you to see how the pattern works. So it's just a, b, and c on top of each of these linear terms, although this is a linear term squared, so it feels a little different when you're working with these. So all right, that's really the setup, and so our goal is very clear here. We want to find, we know a, b, and c exist, we just want to find those. And again, chapter 8 is systems of equations, so we're going to enter the realm of systems of equations. The LCM is just this denominator. I'm going to multiply by the LCM. If I multiply both, each term by the LCM, well, it's just going to cancel the entire denominator in this one, and I'll just get x squared. If I multiply the first term, just the x minus 5 will cancel, and so I'm left with a times x minus 4 squared. If I multiply the second term, 1 of the x minus 4's cancel, but I'm left with b times x minus 5 times x minus 4. And then if I multiply the last term, the entire x minus 4 cancels, x minus 4 squared cancels, so I'm left with c times x minus 5. This is just multiplying. It's not even really doing the multiplication, it's doing the canceling involved in the multiplication. So there's a lot of work going on here. I am factoring, I'm multiplying out the polynomials here where I can. And it takes a few steps. And remember what I'm trying to do? Well, the same thing I did last time. I want to package these into a polynomial on this side where I know the coefficients. The coefficients of x squared is 1, coefficient of x, since there's nothing there, it's 0x, and the coefficient, the constant term, or the degree 0 term is 0. So if I think of x squared as 1x squared plus 0x plus 0, that's going to help me give me these coefficients. Rearranging everything here, ax squared plus bx squared, I can write it as a plus b x squared. And looking at the other side, I know that a plus b has to equal 1. Collecting all the x terms, this minus 4ax, this plus bx, this plus cx, putting all those together, looking at the other side, I know that this has to equal 0. And this last term, which kind of took up 2 lines here, has to equal 0 as well. So what does that look like in a chapter 8 style system of equations? It's like this. Now, we could solve this, well, in fact, I say this with this long sentence here. We could solve this by expected methods such as the elimination method. However, because of where this came from, because this is partial fractions and we have linear terms, which is the only ones we're going to have in this class, we can apply what I call the forbidden values method. All right. I don't think it's, I don't know what other name it has. I'm sure not too many people call it that, but I said it earlier, our job is not to do a lot of work. It's not necessarily our job, although there's still quite a bit of work left. But our job is to find A, B, and C. And if there's a bit of a shortcut to find A, B, and C, we should use it. And here is the shortcut. It's what I call the forbidden values method, and let's back up to why I would call it that. All right. we have practiced, we've done a lot of stuff with things like this. And we've mentioned, we've talked about the domain. We are not allowed to have x equaling 5 because that would divide by 0, -5, sorry. It's very important that I don't get that wrong. -5. And x cannot equal 4 in both of those situations. So we have two forbidden values. Now, it would be great if when you're looking for three numbers, you have three forbidden values, because what typically happens is each forbidden value gives you a letter. So I'm not saying what letter it's going to give me, but the forbidden value of -5 is going to reveal either A, B, or C. And the forbidden value of 4, typically, it's not, there's no guarantee, might reveal, again, either A, B, or C. But I don't want you to overemphasize this method because it's never going to, well, sometimes it will, but you can't guarantee it's going to reveal all of the letters you're looking for. All right, so back to this. Why do I call it the forbidden values method? And why am I looking here? Well, when you compare this equation with this equation no longer has forbidden values because I cleared all the fractions. There are no issues with the denominator. I'm going to take these forbidden values and plug them into this first line. And it's very important you do it the first line. Don't do it farther down the line. It's not helpful. You want to do it before you got rid of the parentheses, before you did any multiplying. All right, so that very first line. So here is a recopy of that first line after I cleared fractions. And I decided to use my forbidden value of 4. All right, so a forbidden value of 4 would make this, I think you can see it. Well, I put it in. If you put in x equals 4 for everywhere there is an x, do you see that it makes this 0? And it makes this 0. The forbidden values are forbidden for the very reason that they make one of the factors 0. So with all those zeros, if that's 0, this whole term's 0. If that's 0, this whole term's 0. So with all those zeros, the only thing that survives the x equaling 4 is this c times 9, or 9c. Of course, 4 squared is 16. So do you see what happened? When I put in x equals 4, the a dropped out of the equation, the b dropped out of the equation, and I get c equals 9/16. That's a huge advantage to solving something like this. I mean, I could just drop that in, and that would simplify things. Actually, if I was really lucky, I might have gotten A or B, and I could have just dropped that in and calculated, if I knew B, I could calculate A right away. Well, it gave me C, and C is, always has two neighbors. So that didn't really crack the case wide open, but we're not done. We have a second forbidden value. X equals -5. So if I let x equals equal -5, you might even be able to see it before I substituted it. Right? This would be 0. This would be 0. The only letter to survive would be A. And the reason why it's -5 is, well, if I put a -5 in there, this becomes -9 squared. So -5 squared, again, I'm just replacing all the x's with -5, taking advantage of all the zeros it creates, and it gave me this really tiny equation. 25 equals 81a. A equals 25 over 81. I just want to enjoy how much I've accomplished here before I continue, but you do have to continue. We know C, we know A. We could go back to the system and solve it whatever way we want, but look at this line right here. If I know A, if I copy that down, since A plus 1 equals B from the analysis I did earlier, right? And if A is 25 over 81, I can pretty quickly find that B is 56 over 81. So all of that work, what does that suggest? That suggests that, in order we found them, A is 16 over 9. What did we find yet? I'm sorry, C is 16 over 9. So 16 over 9 has to go over the x minus 4 squared. A was 25 over 81, and B was 56 over 81. So that would be partial fraction decomposition, but with a bit of a major twist. Definitely take advantage of this method of not just looking at the system of equations and solving that, but also using your forbidden values, or the values that give you zeros in such a way that the letters drop out. The letters that you're trying to solve for, if enough of those drop out, you get an answer. All right. Well, I'm not surprised. This video's come kind of long, so I'll pause it. This one might have 3 parts to it now that I think about it, so we'll pause it right here. But that's section 8.5, part 1.